So, in section 5, we're going to be talking about types of symmetry. So, there are 3 major types of symmetry that we're going to talk about here. So I'm going to abbreviate the phrase with respect to as WRT. That's a common mathematics abbreviation since it's a phrase that happens regularly in definitions. So I'll abbreviate with respect to as WRT. So consider the function, I shouldn't say the function, consider the relation x equals y squared. We'd say this function is symmetric about the x-axis, because if I take one side of that function, one side of that relation and reflect it across the x-axis, it gives me the other half of the function, relation. I keep doing that. Excuse me. This is a relation, not a function. Does everybody feel okay about that? Okay. So if we have symmetry of the x-axis, what do you suppose the next one is?
Symmetry of the z-axis.
Yeah, symmetry with respect to the y-axis. So what is that going to look like? Something like this. And in much the same way, if I take one half of this graph and reflect it across the y-axis, it lies on top of the other half, right? Okay. The third type of symmetry is 180-degree point symmetry with respect to the origin. Where something like y equals x cubed is an example of that. The way I like to think about this is if I take one half of the graph and I perform a reflection across the x-axis and then a reflection across the y-axis, I should get the other side, or the other half of my graph, in either order, whether I did x first then y or y first then x. Everybody okay with that idea? Okay. So the question becomes, okay, we have these 3 types of symmetry. I can identify them geometrically, kind of, by just looking at them. It's a little difficult to exactly verify that I have, a reflection across the x-axis, or is it just really close to a reflection across the x-axis? Or y-axis, or origin. What we'd like is an algebraic way to test this that doesn't require like mega accurate graphing and is a little bit more precise than just using our eyes to determine this. So in the first case, what this means is that f of x should equal negative f of x. And we'll do some examples to kind of show you how we're going to use these algebraic definitions here in a moment. When we talk about things symmetric with the with the y-axis, we call these guys even functions, and algebraically, we have that f of negative x equals f of x. And in the last case, we called these odd functions. And algebraically, we say that f of negative x equals negative f of x. So, worth noting are these three categories of symmetric about the x-axis, symmetric about the y-axis, and symmetric about the origin, inclusive for all functions. If I take all the functions that have those three symmetries, am I talking about all the functions possible? Let me rephrase and ask it a different way. Are there any functions that are not one of, or do not have one of these three kinds of symmetry? Bella, you're shaking your head. Yes, that's absolutely the case. So we can certainly have functions that don't have any of these symmetries. Think about y equals x plus 1. If you draw the graph of that, it's going to look like this, right? That is not symmetric across the x-axis, or the y-axis, or the origin. Right? So it's possible to have none of these symmetries. Everybody okay with that idea? So what we're going to do next is we're going to do some examples of proving whether a function is odd, even, or neither. So when we say prove, are we allowed to just look at the graph and say that's what it looks like? No. What are we going to have to use? That algebraic description. Everybody okay with that? Now, is looking at the graph useless? No, it can certainly tell you which one of the three you should be shooting for immediately. Correct? Which makes it a worthwhile thing to look at, but is not the end-all, be-all for this Let's do some examples here. So let's look at this one. So Sam says he thinks this is even, okay? To prove that it's even, so we'll say claim that it's even. To prove that it's even, we want to show f of negative x equals f of x. WTS stands for want to show. Nope, that was WRT. There's no R for respect in want to show. So, f of negative x, I'm going to basically just make a substitution. So everywhere in f of x, I'm going to substitute in a negative x, just like as if I was evaluating a function. Everybody okay with that idea? Okay. If I do negative x to the fourth, that's the same thing as x to the fourth. Everybody agree with that? Actually, let's do this in a line. That makes more sense in these problems. Everybody agree with that? And x to the fourth plus 1 is f of x. So what have we just shown? F of negative x equals f of x. So it's even. So that line of algebra is all you needed for our proof here. Everybody okay with that? Okay. Let's do another. Let's say we have g of x equals 2x cubed plus 3x. Anybody with an intuition about what this is? Odd, even, or neither? So some people have said odd. If you weren't sure, what could you do? Graph it, take a look at the picture to make a determination whether you think this is odd, even, or neither. Okay? So some people have said that they think this is odd. So what we want to show then is that f of negative x equals negative f of x. Okay? So I'll start with f of negative x. And what I'm going to do is that's going to get substituted the negative x in place of all of the x's, just like if we were plugging a number into this function. Everybody okay here? Nothing tricky happened, right? Now let's do some simplifying. X to the third, or negative x to the third power is negative x to the third, right? And then when I multiply that by 2, I have negative 2x. Everybody agree? Okay. If I do 3 times negative x, I get negative 3x. Everybody agree with that? Okay. I notice now that if I take a negative out, I'm going to just take a negative out. I have 2x cubed plus 3. What is 2x cubed plus 3? That's g of x. So I have negative g of x. That's not a proof, though. But it's not a proof. Can you look at the exponent and go, all the exponents are odd, that should be odd? Yeah, that helps certainly for you to make the claim to know which one to try, but it doesn't help you do the proof. So notice that directions there were quite specific in asking for a proof, so that you can't just go, I'll graph it, I'll just look at it, I'll do, It really then requires you to do the algebra. All right, let's consider h of x equals 4x squared minus 3x plus 9. By the fundamental rule of math examples, we should be able to conclude that this one is going to be neither, right? Because we've done an even one, we've done an odd one. If there was 3 options, like clearly the last example is going to be the last option, right? You don't, but our experience would lead us to believe that that's likely going to be the case. That's fair. So we'll claim here that this is neither. So to do this, we need to show that f of negative x does not equal f of x, and f of negative x does not equal negative f of x. So to show that it's neither, you have to show that it's not even and that it's not odd. It's not so bad. Okay. So we'll start the same way by calculating f of negative x. If I simplify this, I get 4x squared plus 3x plus 9. If I compare this to f of x, they're definitely different. Everybody agree with that? What's different about them? Yeah, the sign on the 3x is different. That's all we needed. They just have to be different in some way, even if it's just like a sign like that. Yes, Sam?
Would it, negative 3 times negative x turn into plus 3x?
Mm-hmm. Yeah, which is what I've written right here. Right?
Oh, I see.
Yep, you're right. Okay? Next, what I'm going to do is I'm going to factor a negative 1 out of this. And I notice that this piece is different. So I know that this is not equal to negative f of x. Everybody agree with that? Now I'm done. Raul? Yes, absolutely. Questions about odd, even, neithers? Okay. Very good. And I believe, at least if you were in my Algebra 3-4 class first semester, we did a little bit of this at the very beginning of the year. It was probably only a day or two, so if you don't remember, it was a long time ago, and I don't blame you. But if it looked vaguely familiar, like, did we do this? The answer would be yes. If you were in my class first semester, we did do this. On to section 6. Which is about asymptotes. Does anyone remember the definition for an asymptote? Perfect. That's an excellent definition. So we say an asymptote of a graph is a line that the graph approaches but never touches. So let's say we want to look at the graph of x squared plus 3x minus 3 over x squared plus 2x minus 3. I'm going to use my calculator to generate this graph. So I'll go to the y equals menu. And I think the easiest way to type something like this in is to use the fraction command. So if you press alpha and the y equals button, it gives you the fraction command n over d, which is just numerator over denominator, which allows you to type in this function without having to mess around with any parentheses. So it's really easy to make sure you've typed it into your calculator correctly. It's easy to kind of goof this up without having done that. If you wanted to try to type this in just in one line without using that fraction command, you need to make sure you have a parenthesis around the entire numerator and then a separate parenthesis around the entire denominator. Yes, what's up? Yes, of course. So either way of writing those is fine. They're both going to give you the exact same graph. I like the fraction command because it looks in your calculator the way it looks on your sheet of paper. So it's easier to kind of error correct that if you type something in wrong. And again, to get that fraction command, if you press alpha and then the y equals button, it gives you those fraction menus. Okay. And then I'm going to graph this kind of in a standard window, so I'm going to do zoom standard on this. Remember that we had just changed our window pretty massively when we did that last domain or maximum minimum problem from the homework. So I needed to reset my window. Zoom standard is a good way to do that. If you're like, yo, my window seems like it's all jacked up, just zoom standard that guy, and it usually gets you something a heck of a lot better. If you don't like zoom standard, sometimes zoom fit works out, but I don't like the calculator to make up its own window because the parts the calculator thinks is important is often not the same parts I think is important. So I'd say like 50-50, it does a good job with the zoom fit command. But zoom standard just resets your window to the normal -10 to +10s. Okay, so if I look at this, I notice there are, how many asymptotes do you see? 2 verticals, right?
Yeah.
And I notice there is one of these horizontal end behaviors, right? We wouldn't call it an asymptote because the part in the middle crosses. Do you guys remember that situation happening last year where we talked about the difference between the horizontal asymptote and the horizontal end behavior? For right now, we won't be so picky as to differentiate the two. We'll, for at least this beginning part of the class, let you use those two terms interchangeably for the horizontals. If you called that a horizontal asymptote or a horizontal end behavior, I would accept either one for the time being. We'll be a little bit more specific later on, but for right now, whether you want to call it an asymptote or an end behavior doesn't bother me. Okay? And I'll be clear come time when I'll start being picky about that. But right now, I'm not so worried about it. Do you remember how we find the vertical asymptotes for a problem like this? Well, let's say that you don't have your graphing calculator to rely on. How would you do this? Find the vertical asymptotes algebraically without relying on your calculator. Which, again, looking at the table is a reasonable way of going about doing it, right? That's fine. But if we're looking at trying to maximize our test performance and like shown work gets us partial credit, it's helpful to be able to like show some work. Andrew? So that's going to get you the removable discontinuity, but starting out by factoring is a great first step. And that's absolutely what I would want to do if I'm looking for the vertical asymptotes. So in the first part, I notice that the numerator, does this factor? There aren't two numbers that multiply to give me -3 that also add to give me +3. So I'm just going to leave that as is. The denominator does, though, factor. Everybody agree with that? So since there is no reducing that can happen, we can proceed to now finding the vertical asymptotes. If there was reducing, we want to make sure we reduce first before we find our vertical asymptotes. To find the vertical asymptotes, I just set the denominator equal to 0 and solve. So I have vertical asymptotes at -3 and +1. And that should match what we saw graphically just a moment ago. Those of you that still have your calculator out, go ahead and take a look. But that does indeed match what we just had graphed. Do you remember how to find the horizontal asymptotes for a problem in this situation? So to find these other end behaviors in a rational function situation, what we need to be concerned about is when the degrees of the numerator and denominator. When the degree of the numerator equals the degree of the denominator, our horizontal asymptote is going to be the leading coefficient over the leading coefficient. So in this case, y equals 1. Sam?
So, degrees, what if there's more than one? Like on the top, we add the degrees together?
So we're only worried about when we say degree of the polynomial, that is just the biggest degree term. So if the polynomial starts with an x to the 5th, and that's the biggest one, doesn't matter what else it has, it's degree 5. Does that make sense? Yeah, you're welcome. Good questions. What happens if the degree of the numerator is less than the degree of the denominator? Does anybody remember what happens in that case? It's always y equals 0. So let's just kind of check that out. So I'm just going to alter what we have here by taking out this x squared. And that 3. So you can see there now the horizontal asymptote. Oops, forgot to change the other one. Don't look, don't look. I forgot to get rid of that. So if you look now, the horizontal asymptote appears to be at y equals 0, right? So we changed it to a degree 1 over degree 2. Do you remember what happens in the third situation? Where the degree of the numerator is greater than the degree of the denominator. This is the one where you get the slant asymptote or oblique asymptote. I don't expect you to remember how to do all these things right now. Okay? This is why we're reviewing some of these things. In general, for this kind of asymptote stuff, if you're able to look at your calculator and figure it out, that'll be fine. Okay? We're not studying rational functions right now, so I don't expect that level of like algebraic precision where you can find these things algebraically and memorize all these little rules right now. Okay?
I'm sorry, if they were equal, you subtract the negatives?
Nope, it's just the leading coefficient over leading coefficient. Mm-hmm. So take your calculator out and try to figure out the asymptotes for this one. Nope, for the one I just wrote down at the bottom. 3x over x plus 1. That's okay. That's okay. So you can do whatever you need to look at that, whether it's graphing it or using the table or whatever. Just use your calculator in your head to figure out what the asymptotes are on this one. So when you type this in, your graph should have looked a little bit like this. If you weren't sure about the vertical asymptote, if you couldn't really tell what was going on, if you press second and graph, you can scroll through the table. Notice the error at -1, which should tell you pretty conclusively that there's a vertical asymptote there at -1, because that's about where it looked like the vertical asymptote we observed on the graph was. If I want the horizontal asymptote, if I look at there, it looks like maybe 3. If I want to confirm that, what I can do is go to my table set and say maybe start at 1,000 and look at the table. And, because I typed it in as a fraction, it's giving me fractions. But if I look at this fraction, what is that almost exactly? Almost 3, right? 3,000 over 1,001 is basically just 3. If you typed it in as one line, it would give you a decimal. I forgot that it does this when you type it in as a fraction. That's only one end of it, though. I should check the other end. So I'm going to change my table set to start at 1,000. And just check the other end to make sure that's also about 3. So 1,000 over 333 is also just about 3. So at that point, I'm pretty convinced that the horizontal asymptote is 3. If you could tell that much just by looking at the picture, that's fine. But if you weren't quite sure, that's how we can kind of use the table to reinforce.